So, yeah, let me start here. Okay. So last time I started to explain a logic circuit. This logic circuit is called decoder. So what I told you last time for this any decoder, so it's a device, logic device. It has any inputs. If it has any inputs, the output here should be 2 to the power of n. Okay. So as an example, if the inputs here, if this one has 3 inputs like X, Y, and Z, so the output here has to be 8 output, 2 to the power of 3. Okay. So here, this is output 0, output 1, output 2, all the way until output number 7. Is that okay? And as I told you before, if you have input number, any input number, this number can have numbers, okay, from 0 until 2 to the power n minus 1. And this is the case. So here we have 3. So here we should have 8, okay? Because this 8 is representing numbers from 0 until 7. Okay? That's what I said. And how it works, it was very simple. For example, let's see all possible cases just for this specific case when we have three inputs. But what I'm explaining here is general. If it has 4 inputs, 5 inputs, 2 inputs, anything I'm explaining is still applicable, but you need to keep in mind the relation, right? So here it is three inputs, so we should have 8 outputs. If we have 2 inputs, we should have 4 outputs, and so on. Okay. So if you have X, Y, Z, as you know, as we explained before, we have here 4 zeros, 4 ones, 2 zeros, 2 ones, 2 zeros, 2 ones, and then we have here 0, 1, 0, 1, 0, 1, 0, 1. Okay, these are all possible cases. Okay, and then because you know this is number 0, so if this is the input, so output 0 has to be 1. Okay, the line number 0 should be 1, and everyone else should be 0. Okay, so this can indicate the number, the binary number at the input is 0, right? Same thing. So always only one output is 1, and all the other lines are 0. Always. Okay. For example, if line number 5 is 1 and the other outputs are zeros, so that means the input here, the binary input here is number 5, and so on. Okay. So in this case, so here the output, I'm gonna call it D0, has to be 1. All the other ones should be zeros. All other output should be 0. Okay. Same thing when the input here is 7. So D7 has to be 1, and everything else is zeros, and so on. So very simple. It's just this device is gonna tell you what is the value in the input, right? Binary value in the input. Okay. And okay, so the way we designed it is for each case we need one AND. So now I have 7, I have 8 cases here. So that means to design this decoder, I need 8 AND gates, right? So one AND gate for each one. For example, if I want to design the AND gate for the first one here, so we have one AND gate this way, and then the output has to be D0. And the input here has to be X prime, Y prime, Z prime, because all of them are zeros. So that in this specific case, when 0, 0, 0 comes, this AND becomes 1, 1, 1, and then I'm going to hit 1 here. All the other ANDs should give 0. Okay? Because this one is designed for this min term. So this is this min term. Okay? For every min term, we're going to have one AND for every min term. Is that okay? So for example, if I want to design this one here, as I said last time, it's going to be XYZ. Okay. If I want to design for this one, as I said last time here, so here X is going to be X because it's 1, Y, Y, and then I'm going to flip Z because Z is actually 0. So it's going to become this way. Is that okay? Any questions? That's what I explained last time. Okay. Also, I explained last time because every AND is representing a min term, right? So if the input is x prime, y prime, z prime, which is one of the min terms, this one is 1. Is that okay? And because as I said before in chapter 2, any function is actually sum of product of min terms. Okay, that is why, as I explained last time, I can use the output of the decoder to represent any function, to implement any function. So to implement any function, all what you need just one OR gate, as I explained last time. So I'm going to go to this one quickly. Yeah. So all what you have to do is for every function, I need only one OR gate. Here we have 2 functions. So that's why I need 2 OR gates. Okay. So the idea is that, for example, if I want to do this one, so this function, this one should be 1 when the input is this min term, or when the input is this min term, or when the input is this min term, or the input is this, any one of these cases. If the input is any one of these min terms, S should be 1. Okay, that's what I did. So all what I did, because I know this output number 1, this one is gonna become 1 when the input is min term 1. Okay, so here I'm gonna 1, 2, 4, 6. So here 1, 2, 4, 6. Sorry, 6. All of them are connected to this one. Okay, so that if any one of these min terms is 1, S is gonna give me 1. Make sense? Okay. And in the coming lab, you are gonna I'm giving you, it's gonna be part of this lab is about the decoder. I'm giving you a function. I'm asking you to implement this function using the decoder. So you are gonna do something very similar to this one. Okay. Any questions? Okay. What's really important for me now is, yeah, as I told you when I designed the decoder, the way I designed it is I have one end for every min term. I have one end here for every min term. Only one of them should give 1, and all the others should give 0s. You got what I'm saying? Because the input is going to be only one min term. It cannot be 2 min terms at the same time. It has to be only 1. Anyway, so what I'm going to do right now, I'm going to explain multiplexer. Multiplexer is a different device, but it is very close to decoder. That is why I want to teach it right now after the decoder. So I'm going to explain what is demultiplexer, what is multiplexer, how it works, and then I'm going to show you. I'm going to use the same circuit here. I'm going to do little modification to convert the decoder to multiplexer, as you will see right now. But let's see what is multiplexer first. Okay, so for multiplexer here, I have only one output all the time. Yes, all the time I have only one output all the time. Okay, all the time one output. Okay, and then here I have here inputs. We call them selectors for selection, or sometimes we call them control bits. Control bits. Okay, so if the number of selectors here, these inputs are in, so I should have another inputs here, which this one should be 2 to the power of n. Okay, so again, I have here only one output for the input. I have an input, I'm going to call it selector. Okay, and then if the number of inputs here for n, so I should have here another input here 2 to the power of n. Okay, now how it works, I'm going to tell you very simple how it works. So here, this input, I'm going to call it input number 0, input number 1, input number 2, all the way, for example, to input number 7. This is if I have here 3 bit. So if I have three control bits, so this one should be 2 to the power of 3, which is 8. Okay. So the point here is that if I put here in the selector number 0, so the input number 0 has to be connected to the output. So the output here, y should equal to input number 0. If input number 0 is 0, the output is 0. If the input number 0 is 1, the output is 1. If the input here, if I put here in the control or in the selection, if I put number one, so actually I'm connecting here, the input number one to Y. Okay. So again, let me say it very simple. So I have 2 to the power n inputs, different inputs, every input 0 or 1 for sure. Okay. And then by the value I put here in the selector, I can select which input is connected to the output. And I can only connect one input to the output. That's why the relation here, if this one is in, I should have 2 to the power 2. Okay? So you can see it like a switch. For sure, it's not a mechanical switch. You can see it like a switch. This switch is going to be controlled by the selection here. Either you connect the input from here or here or here. Only one of them connected to the output. Any questions about how it works? So I have n selectors. I have 2 to the power n inputs, right? Based on the value in the selector. If the selector is number 4, so the input number 4 is connected to the output. If the selection here is number 5, okay, binary number 5. So the selection number 5 is connected to the output. Always it has only one output. Okay, so I can have a multiplexer 2, 4, 2 and 4, right? It can be 3 to 8. It can be 4, 16, but always one output. Any questions? So this is a very important logic device. We use it in too many things. So now, how we're gonna design it? Look at the idea. It's very simple. It's exactly similar to what I did in the decoder, but I'm gonna do little modification as I told you. Look at the idea. So the idea is here for every. Let's see how I'm gonna modify this one here. Okay, so what I'm gonna do here, remember, I'm gonna tell you something important here. Remember, if you have AND this way, for example, and you have here X prime, Y prime, Z prime, as I have just explained. So I told you when the input is min term number 0, 0, 0, the output here is 1. That is decoder, right? I'm gonna see how I'm gonna do little modification on this one to convert it from decoder to multiplexer. Okay. All what I'm gonna do is I'm gonna take the same one here, the same idea, same one here. I'm gonna put X prime, Y prime, Z prime. And these are selectors. This is the selector. Okay. And then I'm gonna put here input number 0. That's it. So all what I did, I'm gonna use the same design, but I'm gonna input number 0 here, input number 1 here, input number 2 here, input number 3 here. But wait a second. How does this make a difference? I'm gonna tell you how it makes a difference. In case of decoder, here, what happened? I had here 1, 1, 1. That's why I got in 1. When the input is 0, 0, 0, okay? So this one's here becomes 1, 1, 1, then I get 1. Is that okay? Look at here. Look at this one here now, okay? Now, if the selectors are 1, 1, 1, that means I selected this one. I'm selecting this one here, or selected this one, or this one, or this one, based on the value of the input. Okay? If I select this one, the output will be I0, I1, I2, I3, and so on. So the idea here is, if you have 1, 1, 1, and then you have here something, I'm gonna call it I0. I0 is a variable, it can be 0 or 1. So the output is actually I0. This is how AND gate works. Okay. So let me see it in a different way. I hope I want to make your life easier. Okay. What I'm saying is, multiplexer, if you understand decoder, you should be able to understand multiplexer because it's just simple modification. Okay. So what I did here in decoder is, I'm gonna put the midterm this way so that only one end turn on and one end are gonna give you zeros. This is decoder. Is that okay? So if the input is 0, okay, so this one is on. If the input is 1, this one is on, and all others are off. Okay. So I'm gonna use the same design, the same thing, but I'm gonna add here one more input here, and then because I have only one output, I'm gonna take all these values together here, I'm gonna OR them, and this is the output. But keep in mind, only one of them is on, all the others are off. So all the, for any case, for example, if the input is number 3, so this one is producing I input number 3, and then this one is 0, 0, 0. So all of them are being 0 except one, the one you selected with the input. Any question? Very important to link the design of the decoder to multiplexer because they are very close to each other. Okay. So for sure, I'm gonna go back, explain everything. That's how I always teach. But now I think it's a good idea after explaining decoder, go to multiplexer, and also because you need it in next step anyway. Okay. So this is how usual. This is a symbol for multiplexer. This is usually a symbol we are using. So as you see here, we have only one output. We have some inputs here. I call them control inputs or selector. Okay. And then here we have, if you have, this one is in, so this one should be 2 to the power n input lines, input line. And all what this one is doing is I'm gonna connect. This one is just to connect this one or this one or this one, only one of them based on what I select here. Is that okay? That's multiplex. Any questions? Okay. I'm gonna show you now how I'm gonna design, how I'm gonna design 2 to 1 line multiplexer. 2 to 1 means the input is 2, okay? And always the output is 1, okay? But here the input is 2. As I told you, as you will see right now, the design is going to be very similar to decoder, but the only difference, I'm going to input I, okay? As you will see. Anyway, so if you have 2 inputs here, so I need only 1 bit for selector, 1 bit, right? If you have 2, that means 1 bit, one bit can select, can give you number 0 or 1, right? So 2. This is a very simple thing. So you can imagine here. I'm gonna make like how it works. As I told you, it's like you have a switch. This output can be connected here, or the output can be connected here. What do you mean by connected? Very simple. I mean, it's equal to this value. If this value is 0, this is 0. If this value is 1, this one is 1. That's it. That's what I mean. It's not 0 all the time. It's not 1 all the time. It's equal. So 1 should equal to this value. Okay. Any questions? So based on the value of the selector here, I'm gonna connect this one here, or it can be here. If it's 0, so it's gonna be connected this way. This one is gonna be, it's not a mechanical switch. I'll just give you this one. It works this way, but it's not a mechanical switch. Okay, how can you design this one? Okay, so here, the way I'm gonna do it, as you see here, I'm gonna have two ends all the time. Now I have 2 cases, right? Only you have 2 inputs, 2 cases. Okay. So for every case, I'm gonna have one end, and then I'm gonna connect everything together using 4. Always will do it this way. So as you will see later now, since a very small one, it's 2 to 1, right? But as you will see right now, I'm gonna give you 4 to 1, and 8 to 1. Okay. So anyway, so in this case, all what I did here, look how it works. Okay, so this is the selector. Okay, this is the selector. Okay, so, and this is input number 0. This is input number 1. So this is for 0. This is for 1. Okay, let's see. When the selector is 0, what do you want to do? So this one has to be connected this way, right? That's what I want to do. Let's see if the logic circuit is going to do that or not. Okay, let's see. So what's going to happen, if this one is 0, so here's the input here is 0. I don't even need to look at this one. If one input is 0, so the output is 0. So this one is off, like 0. Okay. Now, because I have inverter here, so this one becomes 1. So 1 comes here. And as you know from what I taught before, if you have here an input, so So here, if you have an input I0 and 1, so here I'm gonna get I0, okay? And in case of OR, as you need, this is how OR works. If one input is X, one input is 0, so I'm getting the output is X. That's how it works. Okay. So that's why I'm gonna get here I0. Okay. Let's look at the second case. So the second case is when S is 1, when S here is 1, so 1 is gonna come here. This one is I1, so this one is on. And because the inverter here, this one is 0, so I'm gonna turn this one off. Okay. So as you will see, as same thing as explained before, maybe this is a very simple example, but when I go to a big example, it's the same idea. You will see for every case, we have one end for every case. If the selector is gonna output this one, so this end has to be on. That means all of them are ones, okay, and all the other ones should be of zeros, okay, as you will see now. So anyway, so in order to design this circuit here, so here you have I0, here you have S prime, here you have S, you have I1. So this is the relation, final relation. Okay? So it has to be S prime and I0 or S I1. Any questions? This is a very simple one. I'm gonna do the same thing right now, but I'm gonna make it bigger. So now I'm asking you, I told you before, usually in logic circuits, we like to have one input, we call it enable. So that you can have the capability, if I don't want this device, I want to turn it off for some time or some reason, I should have the capability to turn it off, turn it on. We have something like that. Okay. So here I'm asking you, can you do something here to add enable? So this one does not have an enable. Can I add enable? The answer simply is yes. I can do the same thing I did before in the decoder. That's why I'm saying this topic is similar to decoder. Everything is similar. The only difference is that I just an input. I input this one to this and so similar to what I did before. I can modify this circuit to add enable. For example, here I'm gonna add one input here. I'm gonna add one input here. I'm gonna call it enable. Okay. Let's think about it. If the enable is 0, so all of them are zeros regardless of anything, regardless of what value you have in the selector, regardless of I1, I0. This is how AND works. If one input is 0, the output is. Okay? That's why this is like a global switch. So now I'm going to turn the circuit off. I'm going to put here the enable is 0. So all of them are zeros. Why is going to be 0? The multiplexer is not working. Any question? Okay. Now, if I put here 1, okay, so this one now becomes 1. This input is 1. And you know, if one input is 1, it's like neutral. It doesn't do anything, right? Because here in AND, if one input is 1, and then you have X, so I'm going to get X. You got what I'm saying? So when this one is 1, so actually now it can work normally. If the selection is 1, so we have 1 and 1, so I'm going to get I0. Or if this selection is 1, and here this enable is 1, okay, so I'm going to get I1. Okay, you understand what I'm saying? Any questions? Okay, now let's make it bigger. This is just a very small multiplexer. This multiplexer has only 2 inputs. I'm going to make it bigger, but the idea is same thing like what I explained, same thing like decoder. All what I did, I just did 2 modifications. Number 1, all the outputs of the ends are connected using OR. This number 1, okay? Because this one has only 1 output. In decoder, I have 2 to the power n outputs. That's why this output, no OR. Okay? Same thing here in the inputs, I connect I0, I1, I2 for every end. Okay? So let's see next case, which is gonna, as you will see right now, it's just very identical, very similar to not identical, but very similar to this case. Okay. So here I want to design 4 to 1 multiplexer. Okay. So in case of 4 to 1 multiplexer, it means we have 4 inputs, as you see here. And because you have 4 inputs, I need to selector. I need to selector for 4, right? Because the relation is, if this one is n, this one 2 to the power of n. Okay. In other words, to get numbers from 0 until 3, I need 2 bits. Okay. Anyway, So again, it's exactly the same idea. If the input here is 0 and 0, so actually the output here is going to be I0. Same idea as just I have explained. If the input here, for example, is number 2, this is number 2, so the output here will be this way, okay, equal to I2 and so on. And this is, you can see here in the truth table. Okay, any questions? How we are going to make it? Okay, I'm going to tell you how. Same thing as I explained. Okay, now you have 4 inputs. How many end I need? I need 4 ends. One end here, one end, 4 ends, and then everything to connect it using OR. Okay, this is number 1. Number 2. So this is the end for 0. This is the end for 1, for 2, for 3. Okay. So that's why you can see here we have the input here is I0, the input here is I1, the input here is I2, and the input here is I3. Okay. Anything else is actually similar to decoder. So in decoder, I told you what we should have here is S1 prime, S0 prime. Okay, so they have to be 1 and 1. That's why you can see the way I did it for this one. I connected to the prime, as you see here. So actually, this one here is actually is S0 prime, S1 prime, okay, and then I0. This one should give you the first one here. Okay. So this one is gonna be enabled when the input is 0 and 0. Okay, because 0 and 0 is gonna be 1 and 1. I0, I'm gonna get I0. Okay. All other ones are off. Okay, so this is for one min term. Same thing for the other ones. So for example, if I want to design this one here, which is the last one here, so if you see what is the input is actually S0, S1. Okay, there is no prime, and then here I3. So that when the input is 1 and 1, I'm gonna get I3 here. Okay, so if you do this way, this is the output I'm gonna get. Look here. This is in case of 0, 0, it's going to be prime, prime. So in case of 0, 0, and then I0. You understand what I'm saying? So this is a min term number 0. This is a min term number 1. Min term number 2, min term number 3. Is that okay? If you remove these ones and you remove the OR, it becomes a decoder. Right? It becomes a decoder. So this is one output. So I'm going to multiply the min term or end the midterm with I. Any questions? Okay. Let's talk about one more. 8 to 1. Okay. So when I have 8 inputs here, 8 inputs, how many bits in the selector I need them? I need 3. Because the relation, if this one is in, this one 2 to the power of n. Okay, so I need, it is 3. This one should be 2 to the power of 3. Okay, so that this one should give the 3 bits should give me values from 0 until 7. That's it, very simple. So that's why here I have from 0 until 7. Very easy. Okay, how can you design this one? It's the same thing. We need one end for each one case. For every one case, we need one end, and then everything is going to be ordered together. Okay, and this is the result is this way. Okay, but wait a second. So let's design, for example, here, the end of 0, the first case, 0, 0, 0. I want to design this end. Okay, so this end should be, here it's actually A, B, C. Should be A prime, B prime, B prime, C prime, and then here I0. That's it. And this is exactly the first case here. Okay, let's do for number 5. For number 5, okay, when the input is number 5, so number 5 is actually 1, 0, 1, right? And this is again A, B, C. So actually it has to be A without prime because it's already 1, B prime, C, and then I5. That's it. Okay. So for every min term, we have one term here. So this is for 0, this is for 1, this is the min term for 1. So very simple. So if the input is 1, this 3, 1 becomes 1, 1, 1. And all other ones should be 0. There is for sure one of them should, at least one of them 0. All of them are 0. Okay? And when this one is 1, 1, 1, so the output is going to be I1. So all of them are the same. Any questions? This is yeah. So this is, I think this is the chip you are using, or this is one of the chips we have. Nothing is yeah, I think they are going to use this chip in the course, in the labs. 151. So this one has 8-to-1 multiplexer. Okay, this is a chip 8-to-1 multiplexer. So here, as you see, pin number 4 until here pin number 12. So these are 8 inputs. And then here you have EBC, which are the 3 selector. I have 3 selectors. So it's the same thing like this one here. I have 3 selector, and I have 8 inputs and have only 1 output. Yes, that's exactly the same thing. So I have here inputs here. 8 inputs are here. These are the 8 inputs. These are the selector. Okay. On top of that is a chip. It has an enable, as you see here. So okay. So this is enable. Let's look at the enable here. So I have enable here. Okay. Can anyone tell me when you see a bubble this way, what it means? What it means? It means active low. Active low. To activate the enable, the input has to be low. Okay? So this means active low. So that means if I want to enable it, I have to input 0. Active low. If there is no bubble here, if it is connected this way, we'll call it active high. Active high. So to enable, you have to input high. So you have to input 1 in this case. Okay. But in our case here, 0. Okay, that's okay. For the output here, actually, this chip is giving you 2 types of the output. One output here, active high. The other one is active low, which is, so the difference between, so it's going to give you the input G. So one of them is going to give you the same input here. The other one is going to give you the complement of the input. You have to, whatever, it depends on what you want. Don't tell me, do I need both of them? It depends on what you want to do. Because I'm saying you may only need one of them. But it's giving you connected. Here, the output is equal to V0 or V0 prime. You have both. Okay, you can take whatever you want. Based on what you want to do. Okay, so now let's try to understand how this one works from the truth table. This circuit is not different from what I have just explained, but let's look at the truth table here. This is the enable. If the enable is 1, that means it is disabled. So regardless what values you input here, the output is always 0, and this is the complement. So this is the output Y, and this one always the complement of Y. Okay. Anyway, so it is disabled. It's not working. Okay. But if it is 0, that means now it is enabled. So now it's gonna work as multiplexer, normal multiplexer. So if the input is 0, number 0, so here the output is D0. Okay. And for sure, this is always a complement. If the input here is number 1 to 4, number 4, so the output is going to be equal to D4, and so on. If the input here number 7, should be D7. Any questions? Okay, any question? Okay, now I'm gonna similar. So again, guys, I explained, you should understand what is encoder. Okay, how we designed it, very simple. Number 2, you should understand how I modified simple modification of the decoder to make it multiplexer. And what is the meaning of multiplexer? You should understand the concept, the definition. What is it's a definition. What is multiplexer? Okay, multiplexer, I have 2 to the power n inputs. I have selector. It's like you select, switch, you select. Do you want as an output to get input from here or here or here, like a switch? So similar, as I explained before, a decoder can be used to implement any function. That's what I explained in decoder, right? Same thing for multiplexer. Multiplexer can be used to implement any function. I'm going to tell you how. Okay? This is what I'm going to explain now. So I'm going to skip some parts here to go this one. Yeah. So here, how can you implement any function using multiplexer? Okay, guys? Okay. Let's think about the naive way first. Very naive way. Okay. Assume I have this function here. This is a truth table. it has nothing to do with multiplexer. This is function, similar to what we did before. Function, it's a function. When this is the input x, y, z, the output has to be f. This is the output of the function. It has to be this. Is that okay? Okay. How? What is the naive way to implement it? The very simple way to do it is the very simple way. Okay, I'm gonna make this one selectors. So the input of the function is gonna connect it to be selectors. So now I have here selectors. This is f. This is the output of the function. And now I have three selectors here, which is x, y, z. Very simple. And then here I have input number 0, input number 1, input number 2, all the way until input number 7. Is that okay? Okay. I know from the multiplexer, if I input here 0, 0, 0, so f here is going to be connected to here. That's what multiplexer is going to do, right? So what I'm going to do now is, okay, when the input is 0, 0, 0, I want to get 0. So all what I have to do, very simple. So I'm gonna put here logic 0. So that when the input is 0, 0, 0, the output here, which is this is the function, is connected to this one, give me 0. Because that's what truth table is telling me. When the input is 1, I want to get 1. That's what the truth table is telling me. Okay. So in this case, I'm gonna put here 1. So all what I'm gonna do, I'm gonna just copy this one here. I put it here in the input here. So that when I have any input like this one, so I'm gonna connect to this input and I'm putting there 0. You understand what I'm saying? So here's the output of the function, the output of the multiplexer. This is the function, the output of the function. The inputs here, this is the result I want to get for each midterm. So for 0, if the input is 0, 0, 0, that's what I want to get. If it is 1, that's what I want to get. If it is 2, that's what I want to get. Okay. And now this is selected. So based on these values, I'm going to connect the output to 1 which is good. And I already put the result here. That's what I want. This is the result of the function for this input. You understand what I'm saying? Very naive, very simple way. Okay. So if you go this way, if your function, if I go this way, I'm going to do modification on this idea, but this is a very naive way. If I go this way, that means if you have 3 variable function, so that means your multiplexer should have 3 selectors or 8 inputs here. Is that right? 8 to 1. It has to be 8 to 1. If you have 2, so you should have 2 selectors. If you have 4, should have 4 selectors. So the number of selectors should equal to the number of variables. Is that okay? I'm gonna show you a trick right now. I'm gonna show a little bit more. That's why I'm calling this one naive. So I'm gonna show you a modification so that if the input is 3, I need a smaller multiplexer with 2 instead of 3. Okay, so this is the naive way. If the function has 3 variables, so I need multiplexer with 3 variables. So I'm gonna show you now how can I do a little bit modification so that I can, for the same function, I can use a smaller multiplexer. Okay, I'm gonna show you. But before I do that, just related to this idea, I have an example here. So for example, I explained before addition. How can you do addition? This is for full adder. I explained full adder before. So this is x, y, and cn, the carry in, and then the output is sum and the carry out. So now I want to use the very naive way using multiplexer to implement these 2 functions. So as you see here, the way I did it, as you see here for the summation, in the input here, I put x, y, cn, the three variables. Is that okay? And then, as you see here, I'm gonna just copy. I'm gonna copy this one, put it here. So when the input is 0, 0, 0, I want to get 0. So I'm gonna put here 0. When the input is 0, 0, 1, 1, in this case, I want to get 0. So I'm gonna put 0 and so on. In case of 1, 1, 1, I want to get 1. So I'm gonna put 1 this one. Okay. Same thing for the carry here. This is a very simple way. So the very simple way, the number of cases you have should equal to the input of the multiplexer. In other words, the number of selectors here, or the number of bits of selection should equal to number of variables. Okay, you understand this one? This is a very simple one. Now I'm going to show you another way, so that I can use a smaller multiplexer. So here in this case, instead of using 3, I'm going to take only 2. I'm going to use only 2. So I'm going to reduce it by 1. Okay. Same thing if you have here 4 for variable. So I can use it. I can implement it using multiplexer with three selection. Okay. I'm going to show you how I'm going to do it. Any question? Okay. Very simple. I will see it right now. Okay. Yeah. So here. Oh, okay. So for this function, okay, so for this function, as you see here, I have 3 inputs this way, and I want to implement this function using multiplexer with 2 selectors. That means you have only 4 cases here, 4 cases, and here you have 8, not 4 cases. You see what I'm gonna do? So now you have 2 selectors. That means I have 4 inputs. Okay, but here I have 8. How you will do it? I'm gonna tell you a very simple trick. Okay, so the way I'm gonna do it, I'm gonna connect these 2 for the selector. So the selector has XY. This number 1. Okay, so number 1, I'm gonna this selector is 2, so I'm gonna take the first 2. Okay, and then I'm gonna use this one as input, as one of the inputs. You will see right now. Okay, you will see how. Look here. So when XY equals 0, 0, in these 2 cases, when XY, this is a selection. So that means the output here is going to connect to 0, right? Right? So in these 2 cases, because the selection is 0, 0, in these 2 cases, the output has to be connected to input number 0. Is that okay? That means the input number 0 has to be between these 2 values. Otherwise, it's not going to work, right? So what I'm going to do right now is, so what should I put here? Okay, so what you have to put, as you will see right now, one of these cases, either you put 0, either you put 1, or you put z, which is the third variable, or z prime. Okay, so you are going to use the third variable as input. Yes, so always you are going to connect as the input either 0 or 1 or z prime, always. Okay, but which one I have to select? Okay, you have to select the one that can satisfy the function. Okay, so let's see here. For example, this is the function. This is the function I want to output. We agree already because here it is 0, 0. The output is already connected here. Okay, okay. Let's see. So if you look here, what is the relation between f and z? What is the relation? You will feel they are equal, right? So in this case, if the input is 0, 0, f is equal to z. Right? F is equal to z in this case. Okay? That's why I'm going to put it z. So that when the input is 0, 0, f is equal to z. Because when this one is 0, this is 0. This one is 1, this one is 1. Okay, let's look at the second case. In the second case here, so every 2 here is going to be 1 case. Okay? Because this is liquid. So here, this is number 1. Okay? So in case of number 1, so the function here is going to be connected here. Okay. Now, what is the relation between f and z? Okay. So if you see here, when z is 0, okay, I'm going to get 1. If it is 1, I'm going to get 0. So that means f should equal z prime. So that's why I'm going to put here z prime. Okay. Let's see the next one. Next one, in these 2 cases, okay, this is case number 2. So the output here is connected to number 2. Okay. So in these 2 cases, you see here, if z is 0, I have to get 0. If it is 1, I'm gonna get 0. So no matter what value z has, I have to get 0. So I'm gonna put 0. It doesn't matter what, you always zero. Okay, let's look at the last two cases here. Okay, so I'm gonna connect this one to this one this way. Okay, so now look here, what's gonna happen here. If when z equals 0, I have to get 1. When it is 1, I get 1. So no matter what value z has, always I'm gonna get 1. So I'm gonna put here 1 all the time. Okay, guys. So I'm gonna say it again what I did. What I did now, I already accepted the naive idea. The naive idea is I'm gonna the number of inputs here in the multiplexer equal to the number of entries we have here. Okay? This is the naive idea. But I can use a smaller multiplexer, and that's what I did. You have 8 cases, but I use 4 times 1 multiplexer, as you see here. To do that, again, if you look here, we have 0, 0, 0, 0. Okay? So in these 2 cases, the output is connected to only one input 0. Okay? And then I'm going to see the other variable here. I'm going to make relation between the function and the other variable. Okay? That's why you need to here. I see the relation to get this value for f. It has to be 0. So I'm going to output 0 here. Same thing here. Same thing here. Same thing. You can find in this case, you always either you need 0, the input 0, if the 2 cases are 0 and 0. So regardless of what the value is, always 0, so I'm going to put 0. It can be always 1. You can put 1, or it can equal to z or equal to z prime. Any question? You can, but you have to be careful. So I think the question here is about which one I have to connect to the selector. Okay, and I'm gonna do it in one example right now. So here what I did, I just connected XY to the selector. Okay, but remember, for every input I have 2 cases, right? So these 2 cases, 0 and 0. So these 2 cases are related to input 0. So your question is that, can I connect Y and Z to the input, to the selector, and then use this one? I'm totally fine. But look how this will make a difference. Okay. Yes, you can. So I can use this one here for selector. So I can connect this one to selectors. But now, when the input is 0, 0 here, it will be this case, and which another case, this case. Because this is 0, 0, 0, 0. So these 2 cases are going to connect input 0 to the output. So what should I connect at this input? Let's see. I'm gonna make the function now using these 2. Okay. When x is 0, I got 0. Okay. When x is 1, I got 0. Okay. So no matter what is the value, it's always 0. It's a f is always 0. So if I do this way, so here at input 0, I am gonna put 0. So here I'm gonna put y and z. Okay. Okay. This is a very good like exercise. So I'm gonna do it completely now. So as you see here in these 2 cases, I'm gonna put 0 and 0. So I'm gonna put 0. Okay. Now let's look at the second case. When the input is number 1. When the input is number 1, so I have this one here, and I have this one here. This is number 1 and number 1. Okay, which is here. Now I'm talking about what value I'm gonna put here at number 1. Okay, so let's see. When this one is 0, it becomes 1. When it is 1, it becomes 0. So the relation is z prime. Make sense? Let's look at number 2. Number 2 is here, and number 2 is here. Okay. So in these 2 cases, the output here is connected to here. Okay. Let's see what is the relation between f and z. Okay. So the relation here, when this one is 0, it becomes 1. When it is 1, it becomes 1. So that it means it's 1 no matter what, it's 1. So here I'm gonna put here 1. Now let's look at the last case, number 3. So number 3 here and number 3 here. Okay. So in these 2 cases, the output will be connected here. So what should I put here? Okay, in order to satisfy the function. So you see here, when it is 0, I got 0. When it is 1, I got 1. So it's equal. So I'm gonna put 0. F is equal to 0. You see what I did? Any question? Okay. There is something, you need to notice something very serious or very important. Okay. You know what happened when I used the multiplexer? What happened? Okay, I'm gonna tell you what happened. Now you have a function with 3 variables. Okay. Now, because of using the multiplexer, it became like a function with only 1 variable, which is f equal to z, f equals z prime, f equals 0, f equals 1. So it's like the multiplexer was able to reduce the complexity of the function from 3 to only 1. Something outstanding, especially because as the number of inputs, the more we have inputs, the more it's going to be complicated to design the circuit, because you have too many variables. So the way I did it here is, when I have now f became a function only in 1 variable, c, instead of three variables. You get what I'm saying? That's why one of the things you can do is one of the things you can do, for example, for example, if you have 4 variables this way, okay? If you have, let's explain this one first, and then I'm gonna tell you what I want to see here. Let's have 3. If you have 3 variables this way, okay? This is another example. So as I told you, the way I explained it is, instead of I explained the very naive idea. When you have, now you have 4 inputs. So now I'm gonna get a selector with 4 selections. That means we have 16 here, 16 to 1 multiplexer, 16 to 1. Yeah, this is a naive idea I explained. Or what you can do is, I can cut here, okay, and then I'm gonna make multiplexer for this one, and then f is gonna be function in G. In this case, that's exactly what I did here. I need a multiplexer. This multiplexer with 2 instead of 4 here is gonna be 3, and this one should be 8 instead of 16. A smaller multiplexer. Is that okay? Very interesting to me. Why? It's like what I did. Instead of f was a function in 4 variables, x, a, b, c, d. Now f became a function in only 1 variable. So let's see how we're gonna do it. So now, as you see here, I'm gonna use 8 to 1 multiplexer, 8 to 1. Okay, so I'm gonna connect these 3 to the selector here, this selector here, and now you can see here. Let's case of 0. So this is 0. So that means input 0 is connected here. Okay. So what I did, guys, comparing to the naive idea here, every 2 entries is gonna be one input. But what I did before in the naive idea, every entry was 1 input, right? But here every 2 is 1 input. Okay? Anyway, so now I'm gonna see how I can design the function in this case, and then I'm gonna input it here to, I already know when the input in these 2 cases, f is connected to 0. That's okay. Now, if you look, what is the relation between f and g? The relation is equal. F is equal to g. That's it. Makes sense? So that's why I'm gonna put here g. That's it. Very simple. Let's look at the second case. This is number 1. Number 1 here. Number 1. Look at the relation. It's still equal. So f is equal to g. Okay, so I'm gonna put here g. Okay. Look at number 2. Number 2. Number 2 is here. When this one is connected to number 2, you can see here what is the relation between f and g. Flip complement, right? When g is 0, f is 1. When g is 1, f is 0. So that's why I'm gonna put here g prime. Very easy. Look at this case. What is number 3? Number 3, which is this case here, number 3. Always I'm gonna get 0. Okay, so it's gonna be 0. I'm gonna put here 0, no matter what. Also, number 4, these 2 cases. always 0. So I'm going to put 0 all the time. Number 5. Okay. You can see what is the relation. Equal. F is equal to D. So I'm going to put here D. Number 6. As you see here in these two cases, it's 1 no matter what. So it's 1. So I'm going to make it 1. Number 7, it is 1. So I'm going to put it 1. That's it. Very simple. Any questions? Okay. Let's make one more trick. Okay. Let's make, it's a really very interesting course. So let's make one more trick. Okay. Okay. Now, what I did is, I had a function with 4 variables. But because of using multiplexer, I converted it to a function with only one variable. As I did. Then I use, so this one is actually 8 to 1. Can I cut it more? So can I make it like I'm going to use only two cases here? So that means I'm going to use a multiplexer with only 2 inputs and here 4. So it's going to be 4 to 1. So instead of using 8 to 1, I want to use 4 to 1. Can I do that? Okay, let's see. Yes, you can. And what is the cost? I'm going to tell you what is the cost for that, but I'm going to explain what I mean. Okay. So now what happened instead of making this function of 4, but because of the multiplexer, this function is going to be only in 2. Function in 2. You got what I'm saying? So now what's going to happen is that so now I have a multiplexer. We have only how many cases? We have only 4 cases. Only 4 cases. Is that okay? So when the input is 0, 0, so 0, 0 here is going to become 4 entries because I made more reduction. It's going to be 4 entries, not 2, 4 entries. You know what I'm saying? So when 0, 0, because this is the selector, here. So when it is 0, 0, okay, so the output is going to be connected to this one here. Okay? So the output is going to be F is connected to number 0 here, this one. Is that okay? Okay. So what should I put here? What I should have put here? Very simple. All what you have to do, I need to get function. You have CD here, and you can consider this one like a truth table by itself. You can take this part alone here. You can consider this one like a truth table, and then you can use key maps to get F. F is going to be function in C and D, similar to what we did before. You got what I'm saying? That's why it's really very interesting. But look here, what I'm saying. If you just look at this part here, consider this is like one of the problem I taught in chapter 2. Can you get F using key maps? And consider this like a truth table. Forget everything. This is a truth table. Can you get F? Yeah, for sure. That's very easy. I can get F using key maps, using manipulation. So here F is 1 here and 1 here. So for sure you need to simplify. But even if I don't simplify, very simple. So I can see here this one is 1 here and this one here. So the F it should equal C prime. Here is this case C prime D, or here in this case CD. Okay, and then I can put this circuit here. You got what I'm saying? But for sure, there is a cost. The cost is you need to put some bits at the output. You can do the same thing. So it's the same thing here. You can just repeat it again for number 1. In case of this is the cases of number 1. Okay, because this is number 1. Again, you can get a function, if function in C and D, and you input it here. You input it here. You input it here. Same thing here. Same thing here. You got what I'm saying? So instead of making key maps for 4 variables, now I'm making key maps for only 2 variables. Like I cut the problem into half now. But anyway, but use multiplexer. Anyway, any questions? Let's have more examples on this one, and this is also part of the next week lab. Okay. Here, I give you this question here. I'm asking you here to use, you have 3 variables this way, 3 variables, and this is the function 3, 5, 6, 7. So this is the location of ones. The other main terms are zeros, okay? And then I'm asking you to use 4-to-1 multiplexer. 4-to-1 multiplexer, it means you have two inputs here. Okay, so in this case, that's very straightforward case. So I'm going to use this here. This is the selectors, A and B. Is that okay? And similar to what I just explained, so this is here number 0. So number 0 is going to be connected here. Okay, this is number 1, number 2, number 3. And then I have to get a function. I have to calculate the function. Okay, this F using C. Okay, so if you look at the first case here, F is 0, all the time 0, no matter regardless of the value of C. That's why I'm gonna just put 0 here. Okay, I have another example. If I look this one here, it is equal, right? If this one is 0, 0, 1, 1, so F is equal to C. So I'm gonna put here C. Okay, same thing here. It is 0, 0, 1, 1, so equal. So I'm gonna put it here C, right? Now it is this one. It's 1, no matter what. It's just always 1. Got it? Again, what if you don't understand it? Maybe one of the reasons is still you didn't understand that when the input in these two cases 0, 0, 0, 0, the output is connected to this input. So I have to put something here in the input to satisfy these two cases here. Okay. And what I'm having here is either 0, 0 or 1, 1 or C, or it can be C prime. But here I didn't have C prime, only C. That's what I, based on this function. Any questions? Okay, let's look at this full other here. I give you this example. Let's look at another example here. Again, this is the naive idea I told you. This is a very naive idea, as I told you. If I have 3 variables, so I'm gonna use multiplexer with 3 variables. So it's 8-to-1. Okay, remember multiplexer always 1. Okay, but the input here is 8-to-1. Okay, so this is a very naive idea, this is a inefficient idea. Okay, I just copy here, all of them are here, and then when the input is 0, 0, 0, here the output has to be 0, so I just put 0 here. When it is 0, 0, 1, the output is 1, so I'm gonna put 1 here. When it is 2, it's gonna be 1, and so on. I just copy here, put this one here. Okay, so for every entry, for every one entry here, we're gonna have 1 input here. But if I cut it into half and I tell you instead of using 8-to-1, I want to use 4-to-1, as you will see right now. So you will see it's gonna be 2. It's gonna these 2 entries should be corresponding to only 1 input. Okay, as you will see right now. So let's come to the next part. In the next part here, instead of using 8-to-1, I want to use 4-to-1. Yeah. So similar to what I explained before, I'm gonna cut here this way. I'm gonna use X, Y as input. Here there are X, Y, uppercase and lowercase. It's not different. Okay. So these are the input, and then same thing as I told you. I want to get a relation between the summation and C input. So this is one case. This is 1 input, second input, third input, input number 4. Makes sense? Because here 0, 0. So when 0, 0, so it's gonna be 1 input, 1 input, 1 input. Let's see in this case, this one 0 and this 0, 1, 1. So what is the relation? Equal. So here this is 0, 1, 2, and 3. So in case of 0, it has to be equal. So Cn. Okay. Let's look at this one. Here 1, when this one is 0 becomes 1, 1 becomes 0. So it has to be complement, as you see here. C input complement. Okay. Look at this one. Same thing. It's inverted. So it has to be also complement. Let's look at the last one here. 0, 0, 1, 1. So F is equal Cn. That's why I put here Cn. Let's look at the second one because this one has 2 functions. So now I'm going to focus on C out here. Okay, same thing here. Okay, so this is 1 input, second input, 3 and 4. Okay, Let's look at the relation. You don't need even to think about it. C out is always 0, so I'm gonna put 0 here. Okay. Let's look at this case. This one, when it is 0 and 1, I got 0 and 1, so it's equal. So I'm gonna put here Cn. Same thing here, 0 and 1, 0 and 1. It's equal, so I'm gonna put Cn here. Okay. Last one here, it's gonna be always 1, no matter what. It's always 1. You got it? You remember the question I received from here when you asked me why? What if I want to use this 2 instead of this 1? Okay, this will be the next part. It's exactly the same thing, but instead of these 2 cases are just next to each other here, these 2 cases, one here was gonna one be somewhere else. As you see, it's the same thing. Okay, so I think here, yeah. So here, this is another part of the question. Still, I'm using 4-to-1 multiplexer, but this time I'm asking you to use this part for the multiplexer. So this is the multiplexer. Y and C input. Is that okay? And now I have to get the relation between sum and X, or C out and X. Is that okay? But again, for every input, I should have 2 entries here, because the relation between them is half. I have 8 cases, but I have 4 inputs, so half, right? So that's why for every 2 entries here, I have 1 input here. Is that okay? So for example, if you want to connect to 0, we have 0, 1, 2, and 3. If you want to connect it to 0, okay. So 0 again, I'm gonna cut it here. So actually, this is one of them, and always this one. So in these 2 cases, the output is connected to input number 0. Okay, let's see the relation. So the relation here, this one was 0 and this one was 0. If this one was 1 and this one was 1, what it means? It means it's equal. So that's why I put here equal X. What about here? What about this one here? Let's look, do them. So this one was 0 and this one is 0. What it means? It's going to be 0 all the time. So that's why I'm going to put here 0. Any questions? Okay, let's look at the second case. This is when the input is number 1. So this is number 1 is here, and number 1 is here. Okay, so for these two entries, the output is connected to number 1, which is here, number 1 here, and number 1 here. Okay, so let's see what is the relation again between X and sum. So this one was 1, this is 0. Okay, this is 0, this is 1. Complement. That's why I'm gonna do here complement. Okay, let's look at the second one. This is when it was 0, I got 0. 1, I got 1. So it's the same. That's why I put here X. It's the same. Okay, guys, any questions? Let's look, take one more. Okay, for example, here, if I take, for example, number 3, I have this case for 3, and I have this case for 3. Okay, number 3 is the last one here, and the last one. Okay, so for number 3, as you see, let's when this one is 1, I got here 1. When it is 0, I got 0. So the relation is equal. That's why I put here X. Okay. But if you look at what I did here, it's always 1. No matter what, it's 1. So I'm going to put it here 1. Okay. So let's have a quiz. Quiz is going to be about how can you implement a function using decoder and multiplexer. I will give you a function similar to the mini examples I explained. I will give you a function. I will ask you to use the decoder to implement it, or use a multiplexer to implement it. And this is what you are going to do in the next lab anyway. Okay. Any questions? Okay. Any questions? We still have 6 minutes. 2:15. Anyway. So the next thing I want to explain now is something we call it buffer. Buffer. You should understand what buffer means. I'm going to tell you. We have a very simple problem, and buffer is going to help us to solve the problem. So let's first explain the problem, and then I'm going to tell you how buffer is going to solve the problem. In many situations, I want to connect a circuit to another circuit. In many electronic, and here I'm talking electronic. In many situations, I want to connect a circuit to another circuit. However, I have a problem. What is the problem? This circuit can give me very little current, okay, I1. But this circuit needs too much current, I2. So I2 has to be much greater than I1. Okay. So they are not compatible. I can't connect them together directly. What I'm saying? Because here, for example, you need 20 milliampere. Here I can give you only 1 milliampere. You got what I'm saying? So how can you solve this problem? Very simple. We put here in the middle electronic circuit. This electronic circuit, we call it a buffer. Forget the details, just understand the definition. Because in electronics, you will learn how can you use transistor to do that. It's a circuit, okay? So the circuit is going to help me to solve the problem. That's what we call a buffer. So all what I have to do here, guys, I'm going to connect a device. This device is like a triangle this way, okay? So this is the first circuit. Then I'm going to connect a triangle this way, this way, as you see here. So this is, guys, everything I explain this course is electronic circuit, everything. And nor electronic circuit, but I just hide the thing because it's not the purpose. Okay? Same thing. This one you can use it as a block. Don't forget the details, but this one can solve this problem. You call it a buffer. Okay. So all what you have to do is just to connect a buffer this way. So what this buffer is gonna do, if this one is X, this one is X, the same voltage. Yeah. For example, if this is 0 volt, this one becomes 0 volt. If it is 5 volt, 5 volts. So it's the same voltage as we see here. If the input is X, the output is X. It's the same thing. Is that okay? It doesn't change it. Okay. So if it is logic 0, you are gonna get logic 0. Logic 1, you are gonna get logic 1. It doesn't do anything? No, it does. Okay. What it does is it's gonna take a very small current from here and it's gonna provide too much current here. Make everybody happy, right? So this circuit happy, this other circuit happy. Anyway, but voltage or by the way, one of the labs we had before, I'm not sure if still you remember the term or not, something we call it fan out. What is fan out? Can anybody tell me what's fan out? I will be disappointed if no one knows. What is fan out? If you have an AND gate and then you read the data sheet telling you the fan out is 3, what it means? Fan in and fan out. Fan out is how many, for example, if I buy an AND and the data sheet is telling me the fan out is 3, what it means? It means I should not connect more than 3 here. Okay? This is what we call fan out. So the output here, it should not be connected to more than 3. The maximum is 3. You know what is the reason for that? The reason is still the same problem as the current. So the current provided by this one is not enough for more than 3. Can only 3 or less, but it can't be more than 3, right? So again, we can, as I'm explaining here in this picture, one way to solve this problem, we can just put a buffer here. Yes, by using this buffer, I can put more. I can put more here. Okay, because in this case, I'm gonna take a little current from here, and then I'm gonna output much more current to drive the other ones. Okay, any question? That's so. If you see a triangle like this one, you know how it works. It doesn't do anything regarding the variable input equal output. Okay, input equal output, but it's important regarding the current. Now, there is another type of buffer. We call it 3-state buffer. So the previous one here, this one is just a buffer. Now there is another one. I'm gonna add. It's like I'm gonna add a switch to it. Switch. I'm gonna call it a 3-state buffer. It's a 3-state buffer. It's gonna be the same symbol I used to before, something like that. But I'm gonna add one input this way, as you see here. So I have input, I have output, and then I have control input this way. Okay, quickly. So the idea is that if the input is 0, it's like you turn the switch off, so it becomes like open circuit. Okay, so the output is not connected to the input. So if the input is 0, so it becomes like open circuit. So this case we call it high impedance, okay, or disconnected. But if you put here 1, it act like, so this one quickly. So this one act like one of the two cases. This one either become a buffer or it become like open circuit. Open circuit, okay? Open circuit, when the control is 0, it's gonna be like a buffer when the control equal to 1, okay? Anyway, so I'm gonna continue next time.